Okay, cool. Great. So we're going to start then. Welcome back, everybody. I hope you guys all found this new room okay. Everyone good? Oh, you're all here, so I guess it makes sense. I guess I should be talking to people who aren't here, but that's hard to do. All right, so day 2 of Intro to MPI. So we're going to talk today about point-to-point communication. And in last class, we saw sort of the basics, the very basics of MPI. You know what, I'll wait a minute so that you guys can come and sit down. There's a seat here, sort of up close and personal. Great. So in the last class, we saw the basics of MPI, and we got to do something really cool, which was solve problems with ideal parallelism. So where we didn't need to do any communication, so-called massively parallel problems. If only every problem in all of distributed memory programming and parallel programming was like this, life would be really good. So this is the type of problem you hope to be able to solve, but it usually never works that way. So this is the bad news. The world isn't a perfect place. Sorry to burst your bubble. So processors, therefore, need to communicate with each other in order to get the job done. The good news is that this means that distributed algorithms are much more interesting to think about. So it's not just like, oh, I just have 10 processors, I do 10 different things, and life is done. So this means that we can attack sort of more interesting problems using distributed memory programming. So this should make everyone who likes algorithms in the room smile. So if you're not smiling yet, you should smile. All right, great. So I should also mention a couple of things before we go any further. So if you guys have questions, feel free to raise your hand and or call out if you feel that's appropriate. You know, I want to make sure you guys are getting your questions answered, and I like this to be a little bit more interactive than just lecturing. Also, quick show of hands. Like, so who here has attempted homework 0? Okay, cool. And then of the people that have attempted homework 0, who here has successfully completed homework 0? Okay, so if you haven't completed it, can you like summarize why? Is it because you can't log into the machines, or is it because you got stuck somewhere? Like, okay, so if you can't log into the machines, raise your hand. That's the easiest thing to do. Parallel programming. Okay, so when did you sign up for the class?
I missed the first class, but I don't have trouble to log in the CME on, but I have trouble to log in the shared memory.
Oh, I see. Okay. I'm not sure that, has anyone else tried doing that successfully? Were you able to?
Yeah, I can log in shared memory. On shared memory, you can log in, but you cannot create anything, so there is no real usage.
Cannot create anything?
Like, I didn't manage to create any file on it.
Oh.
My character, so I just built the MPI and did my stuff.
All right, we'll have to talk more about that after the class. I'm curious what the actual issue is. There's some different things about the way that machine is set up, so maybe I just need to explain that to you guys, and then maybe you can use it. But it doesn't have, you know, that's a shared memory system. There's not a network of machines. So for doing MPI programming, it's sort of less interesting. But if you guys want to play around with it at least during the quarter, then feel free to. But it's not so critical that you use it. I was just curious. So the MPI cluster is really sort of where you should be. We might have used it to submit homeworks on it, but I decided not to do that. So, all right. So, anyways, that's yeah.
One of your Piazza posts mentioned a grader. Is that a grader, or what is that?
I mentioned it. Oh, so we were going to use a system called Try, which I didn't get around to setting up for the quarter, where basically you would submit your homework to a computer. The computer would try your code on lots of predetermined examples with correct answers, and then would either tell you if you're good or not, and then if you were wrong, it could, depending on how I wanted to set it up, it would have told you like how wrong you were and why. And so that would have given you an opportunity to sort of like see how correct your algorithms are without sort of me looking at it directly.
That would have been my grader.
Yeah, if you guys really, really want that, I can work really hard to get that set up. It's just that I found that it would be a little bit too weird with this course in particular, just because I can't control the way the output would look, so I'd have to do a lot of extra work to, sort of make sure that your code like outputs the right way, and it would just I think it would just be more of a hassle than it would be sort of a help. All right, so but if you guys do want it, then let me know, and then sort of go on Piazza and say something or something, and then I'll think about it. All right, cool. So, okay, so the good news here, getting back to the topic, the good news is that we can do point-to-point communication. We can do things where sort of there's going to be more than just no communication. So what would that look like? Let's come up with a simple example. Here's the simplest one. So we'll have two processes, the blue one and the red one. And the blue one is going to send a message to the red one. And that message is going to look something like this. It's going to look something like, dear processor 1, here is the integer 7, best processor 0. Right? So this is sort of how like the simplest message would get sent. All right, so how does that actually happen in code? Interesting. This actually happens by this particular function call, MPI send. This is an MPI routine, and it has a number of parameters. All right, so let's see what they are. So can anyone, before I show you what they are, can anyone sort of guess what some of these things are? Feel free to just guess.
Presumably the buffer is the actual data. The buff is the actual data. Count is number of bytes.
Something like that, yeah.
And then data type is some MPI specific data type.
Something like that, yeah. Well, that's true. Okay, so let's.
Just count the number of data type there are.
That would be a good, yeah, that would be a very good guess.
And then buff is actually pointer to the data.
The first
Yeah.
sort of bit, if you will, or byte, if you will, of this data. So what would this thing be? It's probably pretty important to understand. You send a message. You have to send a message to someone else. That's probably the rank of the processor that you're sending to. All right, and then communicator, we know what that is because that's the way you do communication, the mechanism for doing communication. We saw that last class. And tag, that's something we haven't talked about. So let's see what these things are. So everyone was right. You're all very smart. So everything we said was correct. The one thing we didn't know about, the tag, well, that's just what it says. It's a message tag. What that actually is it's a way for you to like specify you can sort of differentiate between types of messages. You can say, I'm going to send a message with this particular tag, and then on the other end, we'll see in a moment, you can try and receive messages with that particular tag. And maybe you don't care about what some of these things are. So we'll get into in a few moments, how to avoid dealing with some of the added functionality of a basic send. So cool. So when we do a send, we obviously have to do a receive. Right? It wouldn't really make sense just to send data and then have nobody receive it. There's a matching function in MPI called MPI receive, and again, it sort of looks like this. And you see, similarly, you have basically the same parameters to it. And then we add one more. We add something called a status. So we're going to get into explaining what all that is. So again, similarly, we have a buff pointer, which really is pointing to the initial address of the send buffer, or in this case, the receive buffer. The typo. The count is the number of elements that we're receiving. The data type is the data type. We'll get into what data type is in a little bit. The source is where the message is coming from. The tag is the same. I was just discussing a tag that you can know to receive. And the communicator is still the communicator, and then we add this extra structure called the status. Is this confusing to anyone so far? If it is, let me know. All right, so cool. So if we don't want to care about the source, MPI provides a way of sort of saying, I don't care who I'm receiving this message from. I just want any source, right? So you put that there for any source. If you don't really care about what the tag is, you can also say any tag, right? If you also don't care about the status object, you can use status ignore. Now, what you might be wondering is what is inside. Well, there's probably a number of things you're wondering. One of which maybe is what is inside of the status object, which we'll get to. But I think probably a more pertinent thing that you probably, if you're a seasoned programmer, you're probably really worried about is what this MPI data type is. And sort of what's going on there. And so to answer that question, so I'll show you a slide in a moment that'll show you all the different choices that you have for MPI data type. But before I say what they are, I just want to, I have sort of a vendetta against this particular thing. So what's going on here is that MPI is a library, right? It's not part of a compiler, as we discussed last quarter. There's no MPI compiler. It's a library that you use to send and receive information. And so therefore, when you do this sending and receiving, it needs to somehow understand what you're sending and receiving in order to actually do it, right? So if it doesn't know that it's sending integers, it may not be able to do it correctly. So this is something fundamental to the type of algorithm you'd have to write at a low level. What's strange about this is that these libraries were written in C at a time when sort of the compiler itself didn't really have anything better anyways. The compiler couldn't determine what a type was so easily. I mean, it had some functionality for it in C, but it wasn't so great that it could just sort of deduce arbitrary types. Now in C++, we're really able to do that pretty much on a whim. But so this is really sort of an artifact, I think, from C programming, from before really modern C++ programming.
Questions?
Yeah.
Why couldn't you just pass a raw buffer and a byte count and then let the application term data type?
That's a good question. You can. You can definitely do that.
I mean,
So there's a, let me go to the next slide and then I'll show you what's going on here. So here are all the choices that you get. Well, okay, I'm going to put an asterisk on this. This is all the basic choices that you get. So for basic data types, this is what you can do. So I have on the left the MPI data type, and on the right the C equivalent of this. As some of you guys submitted to me your homework 0, your last problem in homework 0, we were talking a little bit about what types are and sort of how they're defined and by the standard. So like for example, MPI int here is something that's really just the C int, and so it's guaranteed to be at least 16 bits long. On most computers, on most current modern computers, it'll be about 32 bits, maybe 64, but probably not. Think of these types as being sort of a restriction on what you're really allowed to send in MPI. Now the reality is that, and we'll get into this in a later lecture, is that we can send structs and classes as well. So we can really send arbitrary data within MPI. It's a whole other discussion that I don't want to get into for this lecture. And so we'll see it in lecture 4. But basically there's a way of taking these MPI data types and systematically building them into bigger data types. And there's also ways of getting around that whole system and sort of packing all your data into like a big byte object. There's routines to help you do that, so if you need them. And that will all be in lecture 4. But I should just mention that at the very bottom here, there's this MPI byte, and it's really mapped to a C character. And so if you're familiar with types in C, you're aware that a character is sort of this fundamental unit. It's the smallest sort of amount of addressing that you can do on the system. So if you use a character, you can address like anything really. It might be like inefficient because maybe you have to address seven characters to get your whole object or something. But you can really address anything with character. And so if you happen to have data that you want to send that's contiguous in memory like an array, but you don't know the type of the element in the array, or maybe you know the type, but you don't have an MPI data type for it to conveniently pass to this thing. What you can do is you can cast that object to a character pointer, an MPI byte, right? And then you can send sort of a multiple of the normal size of that array. So they basically take the array and the size of the array and you multiply it by the size of the type that you can't define by MPI, but you have in C. Does that make sense to everyone? All right, cool. So some simple stuff, but nonetheless. So I've shown you send and receive, so now I can show you a little bit of code that uses send and receive. All right, so it's pretty trivial, at least for as far as MPI goes. But we have both processors executing this code, and they both originally set the number 7 to 1, right? And then if you're the rank 0 processor, or sort of the master processor, what you're going to do is you're going to correct this problem, and you're going to set the number 7 to 7. Right? But then you want to tell processor 1 this information, so what you do is you send, use MPI send to send the number 7 to processor 1 by giving it the address of this number. You have exactly one of them, so you do that. And then the type of this thing is an MPI int. Actually, I lied. This is actually wrong, because I made this standard size t, and this is not an MPI int. But suppose I wrote int there, and then it would have been correct. So then the last thing, I guess, that we're going to do here is we're going to say we're sending this to processor 1. We're going to use a tag of 0, and we communicate over the normal world communicator. Meanwhile, processor 1 is saying, well, I'm going to just create a status object and then prepare to receive some information, because I know I got some wrong information when I started this. So I'm going to also receive into this pointer, and I'm going to receive one thing, and it's going to be an int, except it's not. And it's going to come from processor 0, and the tag is going to be 0, and I'm going to do com world and status. Yes?
Could you explain a little more where we are in the code now? What is rank equal to 0 mean? Who has set that? Or
Sure. Oh, so I assume you have, in the lines right above here, I assume you just have the canonical MPI initialize and then get rank and get size. That's all you need to know for context. So just like the hello world that we saw in the last class.
so rank equal to 0 means
So, okay, so the rank of a process, we went over this last class, but the rank of a process is just its ID within the communicator. So if you have 7 processes, right, then they're going to be labeled basically in the com world from 0 to 6. So there'll be processor 0, there'll be a processor 1, 2, 3, 4, up to 6, and that number is just the rank.
so does it mean that processor will always do these things? Because
So just imagine that we have the process, so the process that we're calling that has rank 0, that it's executing this code, right? It's going to come to this line of code, and it's going to execute this if statement, right? It's going to say, my rank, is it 0 or not? It's going to be true, and it's going to enter this block. Since it executes this, it obviously doesn't execute the else block, right? So it skips this code, right? On the other hand, processor 1 is going to do the same thing, except when it gets here, its rank is going to be 1, which is not 0. So it skips the if statement and goes into the else block, right? So you have 2 processors. They execute the same code, but they do different things, right? But I guess in theory, they both have the roadmap for all the other processors, but they're not very good at using it. Does that make sense? Cool.
So can you explain again the type, so size t and MPI?
Oh, yeah, sorry. This is just a typo on my part. Just imagine I wrote the 3 characters int here instead of standard : : size t. Yeah, sorry about that. Yeah, in fact, they don't even have an MPI type for size t. Can anyone tell me what size t is? Is anyone sitting here saying, what is size t? All right, that's really good. So there's a brief digression from MPI, but I think this is super important for people to understand. So if you submitted homework 0's last problem to me, you probably know what size t is because we talked about it. But so what size t is this. So here's a question. So what's the largest number an int can address on a?
Question. So how you submit the homework? You just put it in your folder, or
You just email it to me.
you email the
Code, yeah. Yeah. So, all right. So, right. So, great. So, where were we? Int. Int can address how much? Right. So, what's the largest number an int can address, roughly?
655.
All right. That's the right answer. Okay. It's not really the right answer, but it's really the right answer. It's a little bit of a confusing statement. So here's the deal. So the question is if you go on your computer right now and you open up a text editor and you write a for loop that adds 1 to an integer until it overflows, right? The question is, at what number will it overflow, right? So it won't overflow at the number he just said. It'll probably go much, much higher than that. I said
65,000?
roughly 65,000, which is 2 to the 16. So the reality is, on most computers, it'll probably go up to 2 to the 32, right? But Nevertheless, the C and C++ standard defines an int to be at least 16 bits. So you can't guarantee when you write correct C++ code or C code that you're getting any more than 16 bits. Like strictly speaking, you can't guarantee anything about that int. Right? So many people do this though. They write an int and they expect at least 32 bits, probably more. Sometimes people expect 64 bits, which doesn't even make sense. But so these are sort of significant issues, right? Because if you have, so 2 to the 32 is only like 4 million or something, right? 4 billion, I forget, 4 million. So that's still like, a pretty decently small number. Like on many modern things, you can go past that number, 2 to the 32, right? When you write code. So 2 to the 64, on the other hand, is much, much larger. You'll probably never need to deal with larger than 64-bit stuff for integers. But the issue is how do you write code? Like the bigger issue is not whether or not you need this size, but how do you write code that's sort of defensive, that it doesn't really care what the size of that register is, right? Like that's the ideal thing. And I know you're probably sitting here like, man, this is super boring. Like who cares about if it's 16 bits or 32 bits? But just imagine you were like working for a company and you wrote some code and you put an int in there, and then it ran just fine on your laptop, but then you put it on whatever the critical machine is that makes your company lots of money at every fraction of a second or something, right? And all of a sudden everything crashes and your company goes bankrupt, right? I mean, I don't know if that happens, but I could imagine it's not impossible, right? So the issue is really about correctness, and I guess I'm belaboring this point, but really what size t is it's something defined by the standard to be wide enough for anything that you can address. So if you want to allocate memory and you want to make sure that you can actually address all the bytes in that memory that you just allocated, size t is the thing to do it, because it guarantees that you're going to be able to actually look at those addresses. All right, so I know that's super boring, but I guess if you're like a language lawyer or something, you might appreciate this. I don't know. I think it's sort of important to understand. But all right, so that aside, digression aside, let's go back to the code. So here are some important details to understand about communicating with MPI. Every send that you do must be matched with a receive. So every time someone sends something, there must be a receive on the other end to receive it. And messages themselves are delivered in the order that they're sent, right? So that's a little bit of a confusing statement. It maybe doesn't make a lot of sense right now, but I think this is something good to just write down and sort of understand, is that, so as we go forward in the quarter, we're going to do things where this implication might be a little bit pivotal. So it's sort of important to get this. So the last thing is that unmatched sends and receives may result, big bold may there, in a deadlock, in what's called a deadlock. And we'll get into deadlock at the end of this lecture. So today we're going to really explore the different ways that you can use send and receive, or some of the different ways that we can use send and receive. And then we're going to look at deadlock later in the lecture. All right, so a little bit more on MPI status, because we didn't really address what that is. So it's a structure and it contains some information. And then when I first show this to you, you're going to think this is a little bit strange. So it contains things like this: the rank of the sending processor, the tag of the message that you use, an error code if there is one, or MPI success. And it doesn't actually have this. It's sort of a little bit of a lie, but it gets you access to the message length, so how much that count number, sort of what that was. And you're going to say, that's a little bit weird, because I seem to need to call this function with all that information, more or less, to get this structure with relevant data in it, right? But then I already know it, so why do I need to know it again? Right, that seems redundant. And so this, of course, is useful if you use MPI any source. Then if you don't care what the source is, but maybe you want to just receive any message, but then given what that message was, you want to do something, this is sort of how you would do that. This one, of course, is useful with MPI any tag. And the message length is important because we can sometimes receive larger amounts of information than we needed, right? So just because, so this is sort of a fundamental issue with computers, right? Is if you call malloc in C, in serial, right, and you get a certain block of memory, right? the result of that malloc could be bigger than the amount of memory that you asked for, right? So similarly, like when you call send and receive, you can request to receive a certain amount of information, but you may receive much more than you actually need, right? So you don't get control over some of these issues. So the other important thing is that, okay, so, and I should just mention, so that the structure doesn't actually contain this message length, but you use this particular MPI routine to get access to it. So you hand a status and the data type and a pointer to count, and it fills up this count with the relevant information. All right, so that's how you get that. Yeah?
Can you explain the tag of the message again? Like what's
Yeah, so this is something that it's not necessarily apparent that you'll ever want to use it. Regularly when I write code, for example, it's like I never use it, sort of don't care about it. But sometimes there's situations that occur where you're going to send a lot of messages at once, and then you're going to maybe receive a lot of messages at once, and you somehow need this extra tag information to like sort of differentiate. Maybe like some processor sending you lots of information in little messages, and you need to like kind of receive them and handle them in some way. So these tags are a way of dealing with that. But many times people will use MPI any tag unless it's just sort of convenient to put a 0 or something. And I'm actually, to be honest, I'm not clear what happens if you just always put 0 and ignore. I don't know if that causes any issues or if it I should go check that and find out. But right, so these are things you might want to get access to from within MPI status, and yeah. So as I'm sort of alluding to, it'd be a lot better to sort of get this data before the message, right? So if we sort of had all this information before we received something, then that would be a little bit better because maybe we can control how we receive messages. So there's a way to do that. It's another MPI function called MPI Probe. A lot of MPI codes today, right? So what do? You have to know who you want to receive a message from and what the sort of tag is. And then you can give it a communicator and a pointer to the status, and it'll fill up this status object without receiving the message. So internally, there's some internal details here. What's actually happening when you call these functions is that you're sort of a level away from what's really going on in your network card on the computer. So the message could have already been received, for example. Like when you call probe, the message could be sitting there, or it could be not sitting there. That's sort of the binary choices that you get. So if the message is sitting there, you're in lock. These functions return immediately. All these functions, like send, receive, etc., like they all just sort of do their thing. However, if they're not there, and if it has to wait for something, all the functions that I'm showing you today are called blocking operations. So they just sit there and wait for that thing to show up until it doesn't. And actually, I should caveat that MPI send and MPI receive don't always do that. It's a little bit more complicated. The standard specifies something very, very strange. But let's not get into it for right now because it'll make your eyes bleed a little bit. So the point is that you can use probe. You can, in this example code I show you, to get the status, and then use the status to get the count, and then malloc exactly the amount of stuff that you want to receive, right? And then receive that much. So if the thing sends you extra information, you just throw it away, right?
Sorry, is this dangerous if you call probe and then in between your probe and your receive, somebody else takes your message? Or is that not possible?
Okay, so it's not possible for somebody else to take your message, right? So think about it as like this is an important sort of like psychological thing to sort of wrap your brain around, right? Is that you're writing this code that's the same for every process, but every process is distinct, right? So it's like you've written a play, right? Like you've written Shakespeare, you're Shakespeare, right? And you've written your play, right? You've written Romeo and Juliet, and both Romeo and Juliet can read the script, but Romeo only really reads Romeo's part, and Juliet really only reads Juliet's part, right? And they sort of depend on each other to sort of, like when Romeo's talking, it would be very strange if Juliet was not there on the other side, right? But it's allowed to happen sort of in programming, right? So on the stage we would just fire them or something, but But in programming, that can just sort of happen, right? Of course, I guess if you do this too much, then maybe you also get fired, but maybe Shakespeare gets fired. But yeah.
It seems like the receiver is receiving the message twice. First time in the MPI Probe, and the second time in the actual MPI receiver.
So, good question. So, all right. So it's not that the message is being received twice. So this is what I'm sort of getting at. When you write MPI code, you're really a level removed from what's really happening on the hardware. So what's happening is that on the hardware, usually, and I'm put an asterisk on everything that I'm saying because it completely depends on what hardware you have, right? There's actually a physical memory on the network card for the receive and send buffers, right? So when the message shows up from the network, it just sort of is all of a sudden there in memory. Right? It's actually not on the card, it's actually in main memory, but anyways, these are all hardware details we don't need to worry about. But the message is sort of there, and these functions are just sort of getting at that data. Right? It's sort of saying, I'm going to look in this exact location for information, like the call sort of defines that, right? And then you go there and you look, and maybe the information's there, and maybe it's not, right? And if it's not there, you wait for it to show up, and if it is there, you do something with it. And it happens to be the case that this one doesn't copy that information back to you. I mean, it copies some information, it copies the status, right? But then this one here, this receive call, what it functionally does is it actually has a mechanism and is coded to take the actual data from there and bring it back. And then the implementation is able, at the implementation level, they're able to actually like sort of delete the buffer and then inform the network card to do some magic so that the next message can show up, or that it can reuse that space, basically. And actually, so what's actually happening with all the buffering and all that stuff, we're also going to see that later in the course as well.
So the probe, assuming the probe, if the message is not there, then it will wait. The whole
It will
process,
wait,
the
yeah.
whole process stop, basically.
Yeah,
Right.
exactly. And by the way, that's the same potentially with send and receive. Right, so all of these methods, effectively everything that I'm showing you today is blocking. I'd like you to at least think that in your head, even if it's not really true. So it's possible that it cannot happen because the standard does something a little bit funny here, but let's just think about it that way. By the way, if it's getting really hot in here, you guys can open the back door because it's like really hot in here. Oh, cool. Yeah, I don't know how to deal with that right now, but all right. So we can check for incoming messages without actual receipt of them, and this is useful again for receiving messages of a dynamic type and size. All right, cool. So great. So this is what I want you to sort of have in your brain. We have 4 processors labeled 0 to 3, and time moves forward, right? And as time moves forward, each of these processors, they execute code, right? But now that we have send and receive, this was sort of the state of the art as of last class, and now that we have this send and receive, this guy can send a message to processor 2, who will then magically receive it when he calls the receive. Processor 1 will receive a message from processor 0, who's sending it later in some time, and then maybe down here, then they send information back the other way. And then processor 2 can send information directly to processor 3 again, and then maybe processor 2 sends to processor 1, right? And so this is the style of the code that you will end up writing, right, when you use point-to-point communication. And it, of course, can look way more complicated than I'm making it sound, and the processors aren't smiling. But right, so cool. So right, so let's look at an application of this. I think it's good to always keep in mind what you can do with stuff that seems mindless. So I've shown you send and I've shown you receive, and therefore I've shown you basically enough to do more or less all point-to-point communication, or most point-to-point communication. So what I'd like to do is look at the problem of sorting. This is a fundamental problem for computer science, as many of you are probably aware. So the input to a sorting problem is an array of, let's say, n integers. It doesn't need to be integers, but let's just say they are. And since we're doing this in distributed memory, we're going to have them evenly divided, or roughly evenly divided, across P processors, P machines. And for the simplicity of this discussion, we'll assume that P is divisible by n. If you want to assume that P is the power of 2, then do that. Just make this as easy as sort of a discussion as we can have. So the problem, of course, is to sort the total array quickly without using too much extra space. So the issue is that since I've done, so n now can be much, much larger than the individual amount of, the largest n that can be stored on any given machine, right? So maybe some array you can only get like 1,000 elements on one machine, and now you want to do 10 or 100 or 1,000 times that, right? So that's the sort of problem that we want to address when we sort in distributed memory, right? So and by the way, my personal opinion is that this is sort of the big win for MPI, is that you can now solve bigger problems, right? So I guess in homework 0, I asked you guys to think about problems that you wanted to solve in distributed memory. What I was really hoping to get, which I didn't, to be honest, is a list of actual algorithmic questions that you guys are interested in. And so feel free to think about it some more and send me back a message. So this would be a great example of a problem that you'd want to solve in distributed memory, because regularly you can have arrays that are much larger than the memory for a given machine, and it would be really great to have many computers to be able to just solve this problem. So what I'd really like you guys to do in these homeworks, and I'm going to keep sort of asking you these types of questions, is how do you solve these problems in distributed memory? I'd really like you guys to start thinking about the way in which you should solve a problem. It's just, you can't just always just say, okay, I have 10 processors, I put 10th of the data in each place and then do what's necessary. I mean, maybe the basic communication strategies are not going to be very efficient. So that's part of my goal for this short course, is to get you guys to think about sort of domain decomposition. So we're going to see a little bit of an example of that now. So the problem is that if you look at the normal algorithms that people normally use, like in C, there's something called QSort or quicksort or merge sort. These standard algorithms for doing sorting, while very great for serial algorithms and really great even in multi-thread, they require too much communication in distributed memory. So just to point out where this happens in each algorithm. So for example, in quicksort, what happens is that at every stage of the algorithm, you compare against the pivot element. So now imagine the pivot element's on one machine and all the other elements are on another machine. Then there's a linear amount of communication per iteration. So there's actually sort of quadratic communication costs. Right? And so similarly with merge sort, you start out with the whole list and you divide it in half. And then you do some merging, right, after you sort them. Right? So the merging step there would also require sort of a quadratic cost. And you can try and be clever with those particular algorithms, but you'll how to get those particular algorithms to be sort of less communication, but you'll have trouble. So there's a solution though. There's probably more than one, but this is one that I happen to like. It's called Bionic sort. And I'll tell you what a Bionic sequence is. It's a sequence. It's any sequence of numbers where it's first increasing, like entirely increasing, and then later it's decreasing. So it kind of goes up and then it goes down, right? So it turns out that if you can take your arbitrary sequence of numbers and you can first turn it into a Bionic one, then there's an easy way to sort of sort, or a relatively easy way to sort of sort this using a quicksort-like recursion that doesn't use too much extra space and is reasonably efficient. Right? So the takeaway is that these algorithms, their serial time complexity in the worst case is pretty optimal. Well, except for okay, I don't want to say quicksort is bad, but quicksort turns out to be used even though theoretically it's order n squared. Merge sort's worst case order n log n always, although quicksort's sort of average case complexity is n log n, and it's sort of usually faster than merge sort on most inputs. And so most like standard libraries implement quicksort. If anyone's not familiar with this, then well, if you're familiar with this, then I'm telling you something that you don't already know. But anyway, so Bionic sort by duality, I guess, is slower, right? But it has this better space or communication complexity. So that's why we're going to look at it. So okay, so let's explain it by example. So here's our array. We've got these, 8 numbers, I think, right? 8 numbers, yeah. Here, and let's just for the moment imagine that every single one of these numbers is sitting on a different machine, right? So a different computer has all of these numbers. All right, and so what we want to do is we want to sort this, but what our idea was to first get a Bionic sequence and then turn that Bionic sequence into a sorted sequence. So How do we do this? Well, step 0 is that we say, look, there's a lot of these little small bitonic sequences inside of this array, right? Where are they? They're all just the individual elements on every single processor, right? So I know this is sort of, I mean, it is by definition arbitrary, right? But it's nonetheless true, right? These are all little sequences, and they're all sort of by themselves bitonic. And so what we're going to do is we're going to grow a bitonic sequence out of these little bitonic sequences. And here's how we do it. Step 1 is we want to get slightly larger bitonic sequences. So what we do is we take this input, we copy it, and we say we compare these two, we compare these two, we compare these two, we compare these two, right? So far, this is all stuff that requires no extra space, right? So we just do a swap, and a constant extra space, let's say, right? We just basically do a swap when one is less than the other. All right, so the next step is that, okay, that's illustrating that, right? So the next step is that we repeat this process. We sort of compare and recurse again, right? So, sorry, I'm a little bit confused about my own drawing here. Right, so here's what we did. We looked at these 4 elements, right? Let me go back, just not to confuse you. So we look at these elements here, right? And okay, sorry, now I understand what's happening. So we do exactly these comparisons. The 8, we look at the 47, and we get a comparison, and we see that 8 is less than 47, so we leave them alone, right? So remember, we're trying to now make this step 2 here. We're trying to do recursion. So we've now made these little bitonic sequences, and now we are going to make one larger bitonic sequence. So we can do this now by just comparing these elements and these elements, right? So we just do that, right? Except the problem is that when we're done, we do the same thing over here, just in the opposite order. Is this confusing? Does everyone follow me? All right. So the problem is that we're not bitonic yet, right? So by doing those single pairwise comparisons, we now have sort of undone some work we did in the previous step, right? We've now made these 2 guys sort of in the wrong order, right? So then we sort of recurse the other way back down, right? So we do recursion sort of up and then recursion sort of down inside of this one algorithm. So there's a lot of this sort of thing. And so we have to look at these individual pairs again, and we potentially swap them. And so we do that, right? But now, once we've done that, then now we have this side is increasing, this side is decreasing. And so the fact that we do like sort of a logarithmic sort of binary tree thing to like sort of merge up, but then within each of them we sort of go down, this leads to a log squared factor in the complexity of this algorithm. So that the complexity of this algorithm will be n log squared n. So it's slightly worse than n log n. Of course, I'm not done yet, so you don't know that this is not a sorted sequence. So, but believe me that this will work. I'll show you on the next slide if you don't. But so we have this bitonic sequence, and so now we just sort of have to get sort of a not bitonic sequence and a sorted sequence. So this is bitonic. Ooh, whoops, I messed up the animation. Sorry, everyone. Ruined the joke. Ruined the surprise. Great. So we have a bitonic sequence, and so now we can do a shifted compare and swap. So here's how this works. So as these arrows, these crazy amounts of arrows illustrate, we can just take this element here and compare it to this element here, and this element here, and compare it to this element here, and this element here to this element here, right? We just do exactly those comparisons, right? So what is this? This is how do I know what these arrows are? Well, I have 8 elements. So what this works out to be is a stride of 4, like gaps of 4 across. So this is 1, 2, 3, 4 across. So I do this. I do exactly these comparisons, and potentially do swapping if they're not in order now. And then I recurse on this. So I divide these lists in half, right? I know that this side is always less than everything over here, right? By the way that this algorithm just worked. So I can now solve this problem again, right? So I have these little bitonic sequences, and I just sort of go forward. And then I do this a couple times, and then I'm done, and I have a sorted sequence. And so it's literally like this sort of growing kind of weird thing, and then you kind of come back down again. It's kind of an interesting interesting sorting algorithm. Right. Oh, okay, whoops. So I really messed up the stuff on that slide. Sorry about that. So let's just give you a little bit of pseudocode in case that was super confusing. So I have S is a sorted, S is an array, and it's Bitonic, right? So it looks like this by definition. So I notice that the following two lists that I'll show you are both Bitonic and are ordered in the obvious way. So what I do is I take the 0th element and the half element and take the minimum, the first element, the half plus 1 element, so on and so forth. Take the mins and then the maxes in the other list. And sort of by definition, it's really easy, trivial to prove that L1 will be less than or equal to L2 and that both of these things will be Bitonic, right? So basically I recurse on these two lists and I get this complexity. I see some confused looks. Are people confused? People get it? People wish I didn't mess up the animation on the previous slide. Yeah, I do too.
What is the zero time complexity mean?
So what I mean is just on a single computer, implementing this algorithm just on a normal computer with no parallelism, it would take this running time where n is the number of elements. And actually, this is really counting the sort of comparisons, right? The number of comparisons that will actually happen. But let's just call that the running time. So the point is, though, is that if you look at that algorithm that I just did, everything was sort of fixed, right? And I never really needed to like copy a huge amount of information from one processor to the next. It was just sort of all this constant time, like constant size message exchanges, right? So this is a perfect, great scalable algorithm that you guys can now write, in distributed memory with the information I've just told you. So by the way, it was discovered by this guy Ken Batcher in 1968. And the last problem on your homework that I'm about to give you is to implement this algorithm. And Ken Batcher has a hint for you. His hint for you is to use a special point-to-point primitive that I haven't told you about yet, but I will tell you about Ken Batcher's hint now. So it's typically the case in many point-to-point communication strategies that you have to do a send and a receive sort of at the same time. And for reasons that we'll get into in a few moments, this can cause a lot of issues, right? So what happens when you try and send something, but then you have to receive something, and you can't receive it until you finish sending, but the other person is sort of doing the same thing. So you end up in a deadlock situation. So to avoid some of these issues, there's an MPI send-receive function. So it takes basically a mix of the information for send and receive, and then sort of the communicator information. It sort of does both at once and guarantees that it sort of won't deadlock. So this is a pretty useful function when these sort of situations show up. So it allows you to do simultaneous sends and receives. And there's a version of it that I'm not showing you that, because it's sort of out of the scope for right now, where you can add an underscore replace. So notice here that you're requiring to give it the send buffer and the receive buffer, but potentially you want to use the space you're using for sending to do the receiving. So the underscore replace method doesn't require the separate receive buffer, so you can use that there. So you just have one buffer. That saves some space potentially, right? So as I'm sort of alluding to again, there are different ways to send messages in MPI. So some of the common things that come up are blocking versus non-blocking communication, synchronous versus asynchronous communication, and buffered versus unbuffered communication. And this just sounds like a deluge of different names. It's exactly what it is. And we're going to see all of these things in lecture 5. So just a preview of what's coming up. So to give you an explanation of what all these different things do. But just a sort of cultural knowledge, the things I'm essentially telling you are sort of blocking synchronous MPI calls, right? So the distinctions between all these things will be made clear. All right, so moving on now, slightly different discussion. So let's suppose that we wrote this code. So we do the normal initialize, the normal rank and size, So we have all our processors executing this little block of code here. So if your rank 0, if there's 2 processors, let's say, right, and your rank is 0, then you're going to do a send followed by a receive. But then if you're processor 1, you're going to do the same thing, right? And but at least he's sending and receiving to processor 1, and this guy in processor 1 is sending and receiving back, right? So what happens in this little bit of code? So the sends and the receives are matched, right? There's paired, like I said earlier. So will it result in deadlock? That's a good answer. That's another good answer. I don't know who said it, but that's always sort of the politically correct answer to say when someone asks you a question like that, right? But so if you had to say yes or no, would you say that it would deadlock or that it wouldn't deadlock? It won't deadlock? Oh, well, then you're wrong. It definitely deadlocks, right? So why does this deadlock? That's right. So assuming that, okay, so I should really say that, of course, the real answer to this question is it sort of depends, right? But strictly speaking, this code will deadlock all the time, right? Assuming sort of like implemented to spec libraries. So what happens here is that this processor executes this send. It doesn't return from this call until the message is sort of left, if you will, right? So it's sort of been sent on the network. That message usually won't get sent on the network until there's a receive that's been posted for it. Okay, again, that sort of depends, right? And sort of the way that this all works can sort of vary. Your mileage will vary depending on the computer, depending on the implementation of MPI that you use. But loosely speaking, he won't return from this call, essentially, until he sends. And I'll be very specific about this in a later lecture about how this actually works with and there's different versions of sends and receives, and so what the sort of distinctions are. So this call, you'll send it, but he's not going to execute really until this guy starts to receive it. But this guy starts to send it, and he's not going to exit from it until this guy receives it, right? So neither of them execute their receives, right? So there's a deadlock, right? So this is sort of a bad situation. We have 2 processors, and they sort of go head to head to each other, and they just sort of explode, right? So there's just sort of this happening. So deadlocks are an issue. You're going to write code thinking that you've done it correctly, and then it's going to deadlock. Like I can't tell you how many times I'm like, this is going to work, and then I go and I write the code, and then it doesn't work at all. Right? So sometimes it's even very difficult to understand why it's deadlocking. Right? Sort of the way in which these things don't get paired correctly, as you might imagine too.
Does it return an error when it deadlocks, or it just hangs?
How does it know that something's going wrong? How does it know that just in some time in the future, like someone will just come and like match the receive to it? It's send or something. Can't know. Right?
So it just hangs?
Yeah, it just hangs.
Okay.
I mean, I should say again that there's some. So strictly speaking, the standard defines something really vague. I'll just tell you now, so that maybe it'll be less illusion. So what the standard says about MPI send is that you won't return from an MPI send until the send buffer is reusable. That's the words that it uses. All right, so what that really means is that it sort of just depends on the context of what's happening, right? So if your machine is such that whatever you hand it a buffer and then it copies it to another buffer and then it sends it off, right? Then fine, you return from the sends, no problem. Of course, the matching receives are not, that doesn't solve all problems, right? The matching receive is never like that. By definition, it has to block because it doesn't make sense to return from a receive until you've received, right? At least a blocking receive. So this can be a huge issue when you write code, and we're going to spend as much time as we have left in the lecture talking about it. So actually, I found this quote from. This is sitting inside of a really great algorithms book by this. It's called CLRS, Corman, Leisterson, Rivest, and Smith. It's sort of a really nice Bible for algorithms if you're interested in buying a Bible for algorithms, if that's your religion. And so it says, when 2 trains approach each other at a crossing, both shall come to a full stop and neither shall start up again until the other has gone, right? So the 2 trains show up and they never leave. And this is in fact signed into law in the 20th century in Kansas. And There was supposed to be someone in the room today who was from Kansas, but he didn't show up, so I'm kind of bummed. Oh well. All right, so dealing with bugs. So what are all these things? They're bugs, right? So we're used to bugs. We've written code before. It's nothing new. Let's quickly review what we do when we debug, right? So we examine our source code for errors. This is a great way to find issues, right? You look at the problem and you say, that's the problem. Here's what's wrong with it. Let me fix it. Number one way to fix problems. We add enough debugging print statements to our output that it's very clear what's going on. I must say, actually, this is sort of you laugh at it, but this is actually sort of a really great way to debug, especially with MPI programs, right? And for reasons I'm going to get into right now. So the other thing you could do, if you were a serial programmer, if we weren't thinking about MPI programming, you would say, don't do this. Be disciplined and use a debugger like GDB, right? And inspect the state of your program sort of as it goes forward, compile with debug symbols. So then we would find these bugs, we fix them, and we repeat this process until there's no more bugs, right? That's sort of, at least morally, that's sort of what we do, right? And people say things like test early and often, and I think there's a good quote by somebody that said, I don't know who said this, but it can be virtually impossible to predict the behavior of an erroneous program, right? So this really doesn't solve the problem is sort of the point, right? It just sort of solves all the problems that you can observe, right? Well, you may not be able to observe them all. So there's sort of an art to getting correct code. So let's put that aside for just a moment and then look at sort of classic deadlocks, common failures that occur when writing MPI code. Okay, so one of them we already sort of talked about. Well, we didn't talk about precisely this, but got the idea, is trying to receive data before sending it, right? So you're exchanging information and you're trying to receive something that just hasn't been sent, right? And so you're never going to receive it. And then trying to receive data, okay, this is really the same thing, reworded, whoops, but this was really the other way around. I was trying to send data without the matching receive, right? So you try and send something, but it never sort of gets received, and you sort of sit there waiting to send it. Another common issue is just incorrect send and receive parameters entirely. So like you get the count wrong or the type wrong or something, and now like you receive not enough or too much information. And again, you can incorrectly put a smaller amount, but then receive a larger amount, and then sort of assume the larger amount later, and then sort of bad things happen because the rest of the data might be nonsense. Sort of you have no guarantees on what sort of goes wrong. This is an important one. I don't have a great example of this. I was looking for one before the class. But code which depends on an implementation of MPI, but not on the standard of MPI. And this is sort of like an allusion to like this difference between int and size t. So something that's sort of specific to like the computer you're on or the implementation that you're using, but actually isn't defined by the MPI standard. And it's just sort of something the people who wrote that particular library added on for your convenience. So what can happen is you can be like going off and doing something and you think it works correctly because it works for this particular MPI library on this particular computer, and then you move to another system, right, and you get different errors, right? So something worked somewhere, but then it didn't work somewhere else. And then another one that happens is regularly you'll have codes that work for 5 processors but not 6, or 6 processors but not 7, So these are, and actually a really common one that happens is that things don't work when there's one processor. Right, so these are all cases that like a sort of a seasoned, good MPI programmer would handle, either gracefully or with a heavy hand. If there's one processor, do the following thing that's not at all what the MPI program was. Right, so these are things that you should sort of deal with when you're writing correct code. Whoops, I guess we're going to read that again. Words of wisdom from, again, some seasoned MPI programmer whom I don't remember said this, but many, if not most, parallel programs have bugs in them that are completely unrelated to the fact that it's a parallel program, right? So that's sort of the morbid good news, right? Right? It's that you still have bugs in your serial code. Just because you're using MPI doesn't mean that's the only thing you have to worry about. So your serial code can still be buggy. I know this is sort of maybe a sour note to talk about, but it's true. So when you, let's sort of get back to it now. So now, we want to parallel debug, right? How do we parallel debug? So we use all the techniques of serial programming, right? We examine our source code for errors. We add print statements now that encapsulate rank and size. And we're very careful when we write these print statements because print statements by themselves, there's some amount of non-determinism to them, right? Just because you fire off a print statement doesn't mean that that print statement gets printed at the time that you executed it. There can be a delay. Also, if you have print statements like in C++ that use the angle brackets as like a buffered output, one of those things can execute, but then not the next one, right, in a certain right amount of time. So very weird things can occur, especially when the output from all the different computers is sort of going to the same file, right? You can start seeing the output from one processor, then the output for the next processor, and then it can kind of look like garbage. So you have to be very careful when actually writing your print statements now. So use a symbolic debugger, find bugs, fix, repeat. But wait a minute, I just sort of threw one over on you. Right, how do you use a symbolic debugger now in MPI? Right, so if you think about it for a minute, this is sort of a moral issue, right? So GDB is something you attach to a process. Now I have lots of processes. In fact, I can have tens of thousands of processes if I'm working on a supercomputer somewhere, right? No human wants to look at 10,000 processes in GDB at once. No human has 10,000 pairs of hands to do all that sort of simultaneous work. Maybe, and so to make matters worse, it's not just that you have to look individually, sort of embarrassingly parallelly at 10,000 different terminals sort of in one time. You can actually do that, by the way. That's one way to get around this problem, is to fire off lots of terminals on all the different computers, open up GDB in all of them, attach to all the individual processes. But it's sort of worse. Even if you could do that, right, many times the bugs that you get are a combination of like, well, this guy has to do this in this order, that guy has to do this in that order, and then the following exact things have to occur for me to see this error actually happen. So just by adding in GDB, I've now prevented the bug from even showing up, right? So this is sort of a really big problem, right? So we fundamentally cannot sort of do debugging in some sense in the way that we've done it before. You'd think that with the sort of world of free software out there that some startup idea would be to make a free software parallel debugger. I'm definitely not suggesting this to everybody in the room, but nobody's done this. Nobody's made a good free GPL parallel debugger. It doesn't exist. GDB is sort of the only answer for the free software world, state of the art. The question is, how do we just do this on different computers? And my answer to you today is really not the best one, but it's one that is an answer. It's that non-free debuggers exist. So you can pay people who will give you MPI debuggers. So there's a couple of them. One of them is called Alinea DDT. There's another one by these people at a place called RogueWave. They make something called TotalView. So these are two different packages. It turns out that ICME was awesome enough to get us a evaluation copy of DDT for the class. You can go to this website from Alinea, download this software, and use it. And there's remote clients for OS X and Windows. I think if you're a Linux user, then you just use the regular thing. I haven't actually tried it, but you use the regular DDT as the remote client somehow. And my recommendation is that you do public key exchange for the ICME systems if you haven't already to make this easier to use. So the idea is that this will basically give you a graphical debugger. So you can fire off a job on the cluster with whatever code is in there, right? And it'll sort of step through the code and allow you to see all the processors in one window at once, and give you and try and, as best as it can, sort of show you like the values of every variable at once and the value of, and this can get very difficult to sort of debug, but like there's different views in there that I'm not going to try and sell their product for them, so I don't want to do that, but you can try this product out. We have it for free for the quarter for the various assignments that you're gonna work on, let me know what you think about it. I would say, because people are thinking about buying it. So if you like it, then we'll keep having you use it, basically. And I just want to end with a couple of more things about MPI, and then actually leave you with, if I have enough time, with one interesting question to think about. So in MPI, there are errors that are returned from functions. So like a send can execute, and then sort of have something go wrong with it, right? And then return an error to you. And if you've tried incorrectly to use like MPI run, you've seen a couple of these errors. Like MPI init returns these errors. And so there's a way to actually handle them. There's a way to actually gracefully sort of return from these errors. So if you want to, I don't necessarily advocate doing this, but if you want to do this, if you feel it's appropriate, then you can. So what you do is you call this function here, which sets an error handler on a communicator. I forgot to underline that. So the idea is that error handlers, they're going to control like the function call that happens after an error occurs. So like normally an error would occur in some sense, or at least I think by default it's this. So errors are fatal. So the way the error handler normally gets sort of happens on the cluster is that you'll have something go wrong, and then it'll just sort of crash, and then all the programs will abort. And maybe before you abort, you want to get some critical information about what that error was, so that you can figure out what that bug is, so that you can fix it. If you have 10,000 processes and one of them has an error, then you may want to sort of diagnose that. I mean, it may have nothing to do with your code even, right? But you need to be able to handle it. And so what you can do is you can use this other option, which is defined by the standard, MPI errors return. And so then the error codes actually always get returned to the function, right? And then you can use this thing to use that error code to get the string that actually tells you what's sort of, like somewhere in the MPI implementation, they might have a string that prints out that tells you what's sort of going on. So then you can write code like this. And so you create a character array of the maximum size. You want to know how big that, in C you don't get, this does not store how long this message is, so you have something that stores the message length. You execute some kind of send and it returns an error code, which upstairs you've set with that error handler thing, right? And then if the send wasn't successful for whatever reason, then you can handle the error with this error handler here, right? So then you can get the string, you can print out the error yourself, or do whatever you want here, and then abort. So of course, sort of in these sorts of situations, these are great situations to be in because it actually tells you what's wrong, and so you just fix it, right? Right. So, okay. So with that, we're sort of low on time. So homework 1 is available. I've also put some programs up on the website that need some debugging. Ooh, whoops. I don't know what just happened there. I guess the website's there. This is what I want to actually show you. So this is the URL for the website if you don't already know. So there's some programs up there to debug. You can use the debugger. You can use print statements. You can do what you want with them. So play around with that. Have fun with it. Post on Piazza about them. The homework's up there. There's, I think, a lot more interesting problems than the last homework now that you know some basic MPI stuff. So they're going to be a lot more challenging. So I suggest you take a look at them. Email me with questions. You can't get something to work. You can get something to work. If you want to meet me in person, just write. Instead of just having regular office hours, I'd rather just have you guys come to me with questions. You can. I'm in ICME. You can come and find me there. Okay, so I wanted to leave you before we end. We have 3 minutes left. I want to leave you with a problem to think about. It shouldn't be too challenging. It's a good problem for interview questions. So first question. It's a series of questions. The first question is really easy. I have an array. Oh, this doesn't work. I have an array of n integers, say. Let's call it A. And what I want you to do is I want you to report to me what I'll call all the prefix sums of the number. So a prefix sum, the ith prefix sum, is just the sum of the first I numbers in the array, right? So it's sum of, so it's in fact just the sum. I goes from, or j goes from 0 to I of AI. I want you to print this information. I want you sort of to create this information. So this problem so far is very easy, right? So someone give me an answer to it. Anyone? Answer to this problem. For every I, how would you write this code?
Accumulated add.
Yeah, you just have a for loop. You have a temporary register. You add the next element. All right. All right. So now imagine that this array is really big and you can't store it on a single computer. All right. So you can't write that for loop because it doesn't make sense. But you know, you take the array and you chunk it up into pieces, and if you have p processors, then you have n over p pieces of data on every machine. Now I want to have a similarly, not just linear time algorithm, but I want to order n over p style algorithm, right, that solves this problem. All right, so I want you guys to go and think about how to do this. Talk amongst yourselves, maybe. And then worry also about the communication complexity. Like how much of these P processors, like how does this depend on P? In some sense, I'm not telling you what I want the right answer to. There's really a plus something here that depends only on P. I'm not telling you what that is because it will give away too much of the answer. But worry about what that is. So make that as optimal as you can. And you know, write to me or something if you get the answer. All right, cool. Any questions? All right, cool. I guess you'll have them later, so just write.